All right, hello, welcome to Pomodoro Joe for Monday, March 27th, 2023. Today we're doing LeetCode problem 64, minimum path sum. It's a medium problem. Given an n by n grid filled with non-negative numbers, find a path from top left to bottom right, which minimizes the sum of all the numbers along its path. Note, you can only move either down or right at any point in time. All right, and here's our example. So this is your starting point up here at 0, 0. Y increases as you go down, X increases as you go to the right. So you can only go down or right. And it looks like the shortest path is going all the way right and then all the way down. And it's going to give us a sum of 7. All right, so you start up here. Your destination is down here. Okay, so we'll put 25 minutes on the Pomodoro timer and get started. So this seems like a perfect problem for a recursive solution. The reason I say that is because you can break this problem down into smaller subproblems. So for example, if you're starting at this square here, then the shortest path from this square will be the shortest path from this square or the shortest path from this square. So that means the shortest path from any square is the shortest path, or I shouldn't say shortest, the minimum path from any square will be either the minimum path from the square to its right or the minimum path from the square down. That's pretty much it. And so if you break this down into subproblems, you can say, okay, from this square, let's find the minimum path from the square to the right and the minimum path from the square below it, and then recurse. So from the square to the right, you say, well, what's the minimum path from the square to my right? And what's the minimum path from the square below me? And you keep going until you get to your last square. So this is a great recursive problem. Now, looking at our min path sum, this by itself is probably not the best recursive function. For this function signature, we're passing in an entire grid, which means for every subproblem, we'll be passing in a new grid. I don't think I want to do that. I think it'd be much easier to just keep track of our x and y coordinates, our position within the grid, and then we can recurse on those coordinates. So let's write an internal recursive function for this. And it will just take our current x and y position. All right, let's call this min path sum recurse. All right, again, y is increasing as we go down, and x is increasing as we go across. So let's have our minimum x. Actually, we already know the min, so we just need our max. So we have our maximum x, and that's going to be, let's see here. It's going to be the length of our grid. So our maximum x is the length of our first row in our grid. So the first coordinate in our grid will be the row. The second coordinate in our grid will be the column. So the rows correspond to our y, and the columns correspond to our x. All right, so then our max y, that's going to be the length of our grid. That's how many rows are in our grid. And in fact, since I'm saying this is the max x and max y, we'll make those indices, which means that we need to subtract 1 because these are going to be 0 based, whereas the length is 1 based. So that gives us our maximum x and maximum y. Now to our recursive problem. The first thing we do when we're writing a recursive solution, we define our base case. So what's the base case in this particular problem? Well, that's when we've reached the end, when we're at our very last square. That'll be our base case. It means we're done with this problem set and we can return. So let's see. All right, if our x is the maximum x and the y is the maximum y, we're at the very last square. So we'll just return the value of this square. Oh, but we do y first and then x, because y is the row and x is the column. So it seems a little bit counterintuitive, but yeah, it's y first and then x. All right, that's our only base case in this one. Next, we go to our recursive cases. So we can either go right or we can go down. So let's see, our right value, we'll start that as saying we don't know what it is yet. And same with our down, we don't really know what it is yet. How do we calculate the right value? Well, we need to check if we have a right first. So let's see, if our x is less than the maximum x, that means we can still move to the right. Otherwise, we might be at this edge and we won't be able to go right anymore. So if our x is less than the maximum x, then our right case will be, let's see, the grid at this square. Again, it's y first, plus the recursive call. So min path recurse, I'm just going to copy it. And let's see, our x, because we're going right, we can say is x plus 1, and our y stays the same. So that gives us our right path. So we have to add in our current value at this particular grid space, plus the path to our right. And we'll do the same for down. So now, do we have a down? If y is less than our maximum y, then we can still move down. Then our down will equal our current value plus our recursive call to the down square. So we've calculated a right and a down if we have them. What do we return? Well, let's see, if our right is none, then we'll return down. We don't have any other option. And if the down is none, then we return right. And finally, if we have both a right and a down, we want to return the minimum one. So we'll just say return the minimum of right or down. So that's our recursive function. If we're at the last square, we'll return the value of the last square. Otherwise, we check the right and we check the down, and whichever one is smaller, we'll return that one. All right. So the last thing we have to do is just make our initial function call. So we have to return our min path, some recurse, and we start at 0, 0. All right, let's see if this works. Seems to work. Let's submit this and see how we do. Now, recursive functions are notoriously slow, so it's certainly possible that we're not going to do very well on this, but I have some solutions that we can speed this up using some dynamic programming. Oh, and time limit exceeded. So it was too slow. Wow. Okay, so our time limit was exceeded on this. I guess we'll have to speed this up. All right, so we can use dynamic programming here. So dynamic programming is basically just saying, for a given set of inputs, let's cache the output. If we ever get the same inputs again, we can just return the cached value. We don't have to redo this entire calculation. So let's start with some dynamic programming, and it'll just be an empty dictionary. Our key into this dictionary will be some packaged form of the inputs, and our output will be whatever the output is that we've already defined in these return values. So let's see here. We can say dp starts as empty. Now when we have this, we can say our key will equal. Now we need to package up our inputs. So I'm just going to make a tuple, x and y. Now if our key is in our dp, we've already seen these inputs before, we'll just return what we've stored in our dp. Okay, if we haven't seen these inputs before, well then we're going to have to store them. So let's see, any place we have a return, we'll just set our dp key for this value, and we'll return the dp at that key. Same thing down here. We'll have to say dp at key is equal to down, and then we'll return dp at key, or we can just return down either way. Okay. So that should give us a little bit of a boost. Let's see. Will this be enough? Okay, that's enough to get us past. So now we're doing some dynamic programming in addition to the recursion. The dynamic programming just says for any given inputs, if we've already seen this input, we'll just return our cached return. If we haven't seen this key before, then we have to store the value in that key anytime we have a return. So you just find all your returns and store the value. All right, let's submit this and see if we can pass. All right, and we do pass. Don't do great, but we pass. We get 23% for runtime and 8.7% for memory. So not great. Let's see if we can speed this up at all. So one thing we can do, I was using sort of hand-rolled dynamic programming here. Python actually provides a perfect function for this. It's actually a function decorator. So from functools, we'll import cache. Instead of our dynamic programming, we can get rid of that. We'll just decorate this function with @cache. Now this will do exactly the same thing that we're doing with our dynamic programming, only because it's written, I think, in C, it's going to do it a lot faster than what we were doing. So now we have to go through and fix all these up again. Okay, now we're going to let cache handle our DP for us. Huh, it actually doesn't do any better, it does worse. Yeah, now we're down to 18%. So we did better with our own dynamic programming. Interesting. Okay, let's undo that then. We'll go back to our DP solution here. Sometimes this import is costly, so I'm guessing that's why this was slower. Where else can we speed this up? Let's see, well, this min down here could be better. So we could say, this will be right. Anytime you make a function call, it slows things down, so we can do our own here. So this is effectively the same as our minimum call, only we're doing it without making a function call. 24, it saves us a little bit from 23. Yeah, not a whole lot. 24% is still really low. At this point, it became clear that a recursive solution just wasn't going to be fast enough. Anything I tried gets a little bit of gain, but I really wanted to get to a 90%, and recursion just wasn't going to get us there. So I threw out the recursive solution and worked on an iterative solution. So the iterative solution used a copy of the grid to store our values, just as we cached our values in dynamic programming. In this one, we cached the value in the grid itself. Unfortunately, after building this and trying it, it still just wasn't fast enough, and we were out of time. All right, well, I think that is it. We didn't do so great today. We have a recursive algorithm. At best, we did 23%, well, 24%. 24% for runtime and 8% for memory. So there are definitely better ways to do this. But that's all the time I have today. So I hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code than I did. Because clearly this one sucks.